Hi there. Today we're going to look at reducing radicals, and we'll start with some basic just square roots. We'll look at cube roots. We'll even look at having to rationalize denominators. And so pretty much all things radical here. So let's start off with this first one. Now I've created this chart. Well, I stole this chart off Google, but I want you to understand that you're going to have to be familiar with your list of perfect squares. So be familiar with perfect square numbers and even perfect cubes. Now we aren't going to have to know numbers quite this large probably, but you need to be familiar with these first several perfect cubes. All right, because when we're trying to reduce radicals, what we're trying to do is get as much outside of the radical as we can. And so what we're looking for is something that would square root nicely. So on number 1 here, I'm looking at this number 75, and I'm going to try to break it down into something, but I want to pull out some part of a perfect square. So when I look at that, well, 25 will go into 75. So what I do is I break that down into the product of the square root of 25 and the square root of 3. So 25, and I'm multiplying in there, so 25 times 3 is 75. But the reason I break it down is because the square root of 25 is a perfect square, so it's going to come out nicely to just 5, and then I'll have square root of 3. So what I've managed to do is to get the number underneath the radical much smaller by pulling part of that out, the part that I could break down as a perfect square. All right, so on number 2. All right, so you're looking at what's the perfect square that goes into 18, because you're going to break it down into part of it's a perfect square, part of it's not. So it'd be a square root of a 9 times a square root of 2. Square root of 9 comes out nice, square root of 2 stays put. Okay, so now let's try number 3. Now be careful. You always want to try to break it down as much as you possibly can. And so when you do 72, a lot of people think, oh, that's going to be 9 and 8. The problem with 9 and 8 is that I could write that as 3 square root of 8, but the square root of 8 actually breaks down further because 4 goes into it. So you always want to try to pick the largest perfect square that will go into it. It's kind of like when you reduce a fraction, but you didn't pick the biggest common factor, and so it continues to reduce. We want to pick the biggest perfect square, which in this case would be 36. So we go with 36 and 2. And one way to check that is just look at this number that's supposed to be stuck in the radical. And if you look at that and decide, well, that can reduce farther, what that means is you did not pick the biggest perfect square. And so you might go back and find something bigger. If 4 goes into a number, I always check 16, and I might go to 64 and sometimes 36. All of those kind of mesh nicely, so always try to pick the biggest one. Okay, so on number 4 now, this one we're doing a perfect cube. So now when I break it down, I'm not looking to put a perfect square in there, I'm trying to put a perfect cube in there. So I look at my list of perfect cubes and try to figure out what goes into 500. I'm guessing maybe 125 does. And you can use your calculator to kind of help you a little bit, but 125 is going to go into 500 4 times. So I'll put in a 125 because that's the perfect cube. And don't forget that you're putting cube roots on these, not square roots. Okay, so the cube root of 125 is 5, and then this just stays put. It's not a square root of 4, it's a cube root of 4, so that does not break down nicely. And you leave that in your radical. Okay, so let's do a few more of these. Cube root of 135. So we've got to find some perfect cube that goes into 135. And so looking at that, and again, you can kind of use your calculator to help you find some numbers. We don't usually get them to be too large, but on this one, I'm thinking that 27 goes in there 5 times. So 27 times 5. And then that cube root of 27 is just 3. Cube root of 5 stays put. All right, so now let's do some that have some variables in there. What you're wanting to do is to, okay, so let me do a little side note here, and I'll come back and erase this later, but anytime you're dealing with variable parts, you're really just looking at their exponents. If you could square root an n squared, that would work nicely. The square root of n squared is just n. But it wouldn't work nicely to take the square root of n cubed. You're always going to be, when you're square rooting, you're going to be dividing by this index number, which is assumed to be a little 2 here. So 2 divided by 2 gets me an n to the first. Over here on this odd number, it doesn't work so nicely. So we'd have to break it apart to something that works nicely. Since I'm dividing by 2, since it's a square root, I would want this power here to be an even power, and that way it would divide by 2 nicely. If I was going to cube root with a variable, then I'm going to divide by a 3, and so I'm going to want that exponent to be a multiple of 3 when I do it. So on number 6, I'm square rooting. So I'm going to break it down to, this is all going to be the stuff that comes out nice, this is going to be all the stuff that's left. So let's start with the 80, the number. Okay, 16 goes into 80 5 times. So 16 is my perfect square. All right, and then as far as the ends, what you're going to do is going to bring over as many of those ends as you can that are going to square root nicely. So since there's 3 of them under there, and I know that I'm going to be dividing by 2 because this is a square root, then I'm going to want to bring 2 of them over, which means 1 is going to still be stuck underneath the radical. Okay, so this first part should square root nicely to just 4n, and the second part stays underneath the radical. Okay, let's try again. On number 7 here, I have this coefficient that's out in front. I just leave it out there and kind of ignore it until the end. And I'm going to break it, the 27mn cubed, into what's going to come out nice and what's not. Since we're square rooting, I'm looking at my perfect squares to see what goes into 27. And that would be a 9 times 3. All right, then as far as how many variables can I bring out? Well, remember, since I'm square rooting, I want it to be multiples of 2 that I pull out. Since I only have the 1m, it's going to have to stay over here. I can't pull that out. But the n, I could bring 2 of them out. That would square root nicely, which means 1 gets stuck left under the radical. All right, so once you have that picked out, then you have 3, and then this should all come out nice. It's going to be a 3n. And then this last part stays underneath the radical. So that simplifies to 9n square root of 3mn. So that 3 that we had out in front, we just kind of drag it along until it gets multiplied by this part that comes out nice. Okay, so last one, number 8. Really messy one, but nice because we got several things that we're going to have to be able to pull out. This happens to be a cube root. Okay, so we look at our perfect cubes and try to find something that goes into 48, and it looks like it's going to be an 8 times 6. Okay, now as far as the variables, remember that we're cube rooting, so you want to bring out multiples of 3. So as far as the x's, since there's 6 of them and 6 is nicely divisible by 3, I'm going to bring all of them out. Same thing on my y's. I got lucky there. All of those can come out because 3 divides by 3 nicely. On the z's, I don't have enough that would divide out, so I would have to leave the z's over here. All right, so then this will become 8 times, and then let's cube root this. The cube root of 8 is 2, and then you're dividing your exponents here, so 6 divided by 3 would get me an x squared, and then a cubed, y cubed of cube rooted is just going to get me a y, and then this all gets left underneath the radical. So final answer, 16x squared y, cube root of 6z squared. Don't forget to put that little cube on the radical sign as you go. Okay, so I don't have the list there anymore. Hopefully you get familiar with that list. You might need to jot it down on the edge of your paper, your perfect squares, your perfect cubes. We're just going to assume you kind of know those at this point. Let's do some multiplying. All right, so to multiply, you you can multiply anything that's underneath the radical together, and anything that's outside of the radical can be multiplied together, but you can't merge the two. So on number 9 here, I've got the 12 underneath the radical, and I've got the 9 underneath the radical. Now, it's kind of a coincidence that this 9 is here, because that actually comes out beautifully. The square root of 9 was just 3. So in all honesty, I probably would just call that a 3. But I'm going to kind of pretend I didn't notice that and show you how you work these if it doesn't come out quite so perfectly. I'm just going to multiply the 9 and the 12 together and make this one big radical of the square root of 108. And then what I'm going to do is I'm going to re-break it down, but I'm going to choose better factors than 12 and 9, because 12 and 9, neither one of them is a perfect square. Actually, 9 is, but we're pretending it's not. Okay, so what you do is you pick factors that are going to be the largest perfect square that would go into 108, and that happens to be 36. So that's a better choice than 12 and 9. Let's do 36 times 3. All right, so then that would reduce to a 6 root 3. Now we could have gotten there by breaking this down and just calling that a 3, but the square root of 12 would have had to break down, and then we would have had to multiply them together. So either way you do it is fine. Let's look at number 10. All right, so remember, you can multiply things that are outside the radical and things that are inside, but not both. So like this 3 and this 10 can't actually get multiplied because the 3 is outside the radical, the 10 is. This square root of 15, we'd assume there's a 1 out here in front of this. So what you're multiplying are those coefficients. So 3 times 1 would get me a 3. And then I'd have a square root of 150. And then my job is to re-break that down better than how they had it broken down. Let's pick something, rather than 10 and 15, what's a perfect square that goes into 150? It should be 25. Goes in there 6 times. That's a better way because the 25 is going to break down nicely. So then I end up with 15 square root of 6 for a final answer on that. On number 11, I wanted to show you kind of what happens here when you multiply by something times itself. Well, the square root of 8 times the square root of 8 is really just the square root of 64. And the square root of 64, I'm not going to break that down because that happens to be a perfect square. That's perfect. That's going to come out nice. That's just equal to 8. And then I'm done. Okay, notice that when I do that, if I take a square root times itself, all I end up with is that number. It's because basically all you're doing is this. You're taking the square root of 8 and you're squaring it, and the squaring and the square root are opposite operations, and you're left with just that 8 there. Now that concept of multiplying a radical by itself to be rid of the radical is something we're going to come back to. Okay, let's look at number 12. Why don't you try number 12 on your own? Take a minute to pause the video, work through it, and then turn it back on and you can check your answer. All right, hopefully you got negative 3 root 10. And if not, check your work, see where you went wrong. All right, so the next thing that we're going to do is add and subtract. All right, when you add and subtract, you have to have like terms, kind of like when you add a 2x plus a 3x. If you had something like 2x plus 3x, all you're doing is adding your coefficients together, and so you would just call it a 5x. So it's the same deal with a radical. You need the radical parts to be the same. They have to have the square root of 3, square root of 3, or something like that. And then you just add the coefficients. So looking at number 13 here, I can't add these because these are not alike. But I do notice they can both reduce. So let's take some time to reduce, and maybe we'll get lucky. Maybe after I reduce, they'll be the same. So we work individually here. This negative 3, I'm going to break down my square root of 20 to 4 and 5. Minus, I'm going to break down my square root of 45 to 9 and 5. All right, so I end up with a negative 6 root 5 minus 3 root 5. And as I had hoped, now I have common radicals. They're both root 5s. So once you have that, you just work on your coefficient and say, okay, I got a negative 6 and a negative 3. That's going to give me a negative 9 root 5. Okay, let's try number 14. Again, radicals are not the same, but we can do some reducing to help get them there. The 3 square root of 6, can't do anything with that, so I'll just leave it. Minus 3, I can break down the square root of 24 with a 4 and a 6. So that's negative 3 times 2. Okay, I might start doing a little bit of that in my head. At this point, I'm in the habit, because I teach Algebra 1, I'm in the habit of showing every single step. But ideally, by the time you're in college algebra, you should be able to do some of that stuff in your head. All right, so that's going to be a 3 times 2. So that's going to end up being a 6 root 6. And then, since my radical parts are alike, now I can actually merge this into, it's got a 3 minus 6, so a negative 3 square root of 6. All right, let's try one more, and then I'll let you practice one. All right, number 5 here, it has 3 different radicals, and so I'm going to have to work on getting all of those. Now, they don't have to all match, but I'm hoping something will match after I reduce. So here we go. We got a negative 3. Break this down to 9 and 5. Okay, the square root of 24, I'm going to break down to 4 and 6. And then I've got the 3 square root of 6, does not look like that's going to reduce at all. So on this first one, the square root of 9 is just 3 times negative 3 would get me a negative 9 square root of 5 minus 2 square root of 6 plus 3 square root of 6. So I have a couple of these that I can combine because they have the common radical. This one's going to have to be stuck by itself. So I have a negative 9 square root of 5, and then I have a negative 2 and a positive 3, so it's going to be a plus 1 square root of 6, but we don't typically write the 1, and so it'll just look like this. All right, so now it's your turn. You try number 16 by yourself. Pause the video. No, really, you can pause the video. I'll wait. All right, your answer should have been a negative 6 square root of 5. If it's not, take a minute, check your work and see where you might have gone wrong. So the last thing that we're going to do here is division. So we've done the addition, subtraction, we did the multiplication, but when we are dividing by radicals, we have something that we call rationalizing the denominator. In other words, we don't typically like to have radicals in the denominator. If we're going to have a radical, we'd rather it be in the numerator. And so we're going to do the best we can here to try to reduce this so that we don't have a radical in our denominator. So if you'll start with, actually I'm going to look at number 18 first. Let's start there because it's a little bit smaller numbers. Okay, so I've got this square root of 2 that's in the denominator. Well, the thing with the square root of 2, I mean, it's fine and everything except that it's a radical in the denominator. So do you remember earlier when I said we're going to come back to that? I need to multiply by something that's going to get rid of that. Okay, but the only thing I can multiply by without changing the value of this fraction is 1. So I'm going to multiply by 1. But remember that you can write 1 several ways. You could write it as a 1, or 6 over 6, or 10 over 10, or in this case, square root of 2 over square root of 2. When I multiply by that, what that's going to allow me to do, remember you multiply straight across, so I'm going to end up with a 2, because square root of 2 times square root of 2 is just 2. And then on the top, I'm going to have a 2 square root of 10. So that's your first step, is to multiply by whatever the radical is in the denominator. And then you're going to look to reduce anything. So in this case, I've got the 2's that are going to reduce, and then remember that you can't multiply with something that's inside the radical and something that's outside of the radical, and so you can't divide either. What I'm going to be dividing are the coefficients on these. All right, and then you're also going to want to look to see if that radical reduces, and the square root of 10 will not. So I'm pretty much done. My final answer there would just be the square root of 10. All right, let's go back to 17 and try that one. The reason I started with 18 is because the numbers were smaller. On 17, I've got this square root of 12. All right, now there's different ways to work through this problem. You know, we've got, you might just jump right in and multiply by the square root of 12. That's one option. You don't have to worry about the coefficient out in front. You only multiply by the radical part. The other thing you might notice is, gosh, that's just a square root of 4. That's just equal to 2, isn't it? And yes, it is. But, oh, and you might even notice that the square root of 12 could reduce. So there's a lot of ways to approach this. I think what I'm going to do on this is show you another option and try to, again, ignore that this one came out quite so beautifully, because that won't always be the case. But notice that you have a square root of 4 over a square root of 12. If you have a square root of 4 over a square root of 12, that could just reduce to a 1/3. All right, so what happens is this square root of 4 reduces with this square root of 12. Because they're both inside the radical, you can reduce them. So what you actually end up with is a 3 over 2 square root of 3. Anytime you get a chance to try to reduce the radicals first, that's usually a good option because it gets your numbers much smaller. All right, so now I have this problem. It's very similar to 18. I'm just going to multiply by the radical part. And then I'm going to have a 3 square root of 3 over 2 times, notice this root 3 times root 3 is just going to be a 3. So that denominator actually ends up being a 6. Okay, so you have 3 square root of 3 over 6, and then you can reduce the 3/6, not this 3 because it's inside the radical, but these numbers out in front. So a 3/6 is going to reduce to a 1/2, so you end up with root 3 over 2 for your final answer. All right. So now these two problems, 17 and 18, notice that everything was being multiplied inside here. Let's look at one where you have to add. All right, that throws a little kink in it. As soon as there's addition going on, you can't just start reducing things. Now these don't reduce in this case, but if that was a 5, you can't reduce those. Not if you're adding here, because it's this whole quantity that you're taking that 3 and dividing by, and so you can't just pick it apart. All right, so it would be tempting to multiply by root 5 and root 5. That's what we were doing earlier. The problem with that is this root 5 is actually going to have to get distributed. And when I take it times this root 5, it's going to work beautifully, but all that happens is when I go distribute it, now that's going to turn into a 5 times root 5, and I haven't gotten rid of the radical. I've just moved it. All right, so that's not going to be what I multiply by. Actually, what we're going to multiply is something that we call the conjugate, which is the exact same thing, only with the opposite sign in the middle. So since it's a 5 plus root 5, I'm going to multiply by a 5 minus root 5. That's what's going to get rid of the radical for me, but I have to also do it on the top. Now let me show you what happens by doing that. If you multiply that denominator by its conjugate, the same thing but with a minus sign, we actually end up with 2 binomials, so we're going to have to do some FOIL here. So here we go. First times first. 5 times 5 is going to get you a 25. And then you're going to do outer. And that's going to get you a minus 5 root 5. And then you do inner, and that's going to get you a positive 5 root 5. And then last, it's a positive times a negative, so that's going to be negative. And a root 5 times a root 5 is just a 5. In the numerator, since there's only a 3 up here, it just gets distributed. So that'll end up being a 15 minus 3 root 5. Now, let's look at that denominator. We handpicked this conjugate because this is going to happen every time. Do you see how these middle two terms are going to drop out? That will happen every time because we handpick those numbers so that you get the same thing but a different sign. So since these middle two terms cancel out, I really just end up with a 25 minus 5. Okay, so then I have 15 minus 3 root 5 over 20. All right, and then your last step is to look to try to reduce anything. And this 15 and 20 look like they could reduce, but remember this minus sign ties this all together. And so it's that whole thing divided by 20, and the only way I can divide that or reduce is if it goes into both of them. Now, when I say it goes into both, I don't mean this radical. Remember, you can't reduce a radical with something that's not a radical. It would have to be this coefficient here that's outside the radical. So the 15 and 20 could reduce because 5 goes into both, but 5 does not go into 3. So I'm not going to be able to reduce this. I'm done. Okay, so that's a little bit more work when we multiply by the conjugate. Let's practice that a little. All right, so I have this last one. One more time, it's the conjugate. It's an even messier one here because if you look at the numerator, I've got a binomial up there as well. Don't worry about that. What we're trying to rationalize is the denominator. So I take that, and I'm going to multiply by its conjugate, 5 plus root 3. And then you do the same thing on the top, 5 plus root 3. On the bottom, I'm going to FOIL. So first gets me 25. Outer is 5 root 3. Inner is going to end up being a negative 5 root 3. And last is going to be a negative, and a root 3 times root 3 is just 3. All right, on the top, I actually have to do FOIL again on the top. Don't count on this working out quite so beautifully, though. The conjugate helps us in the denominator. It doesn't help us in our numerator usually. Okay, so first would be a negative 5. Outer is going to be a negative root 3. Inner is going to be a 5 root 5. And last will be a square root of 15. All right, let's see what we can reduce. On the top, we unfortunately do not have a single like term. This is just a number. That's a root 3, root 5, root 15. You might think that you can reduce the root 15, but you can't reduce it in any way that's helpful because there's not a perfect square that goes into it. So we're pretty much just stuck with that numerator, just leaving it exactly as is. In the denominator, our middle two terms are going to cancel. That's what we were wanting to have happen. We want those radicals to drop out, and we just end up with 25 minus 3. All right. The only way something could reduce is if there was a 2 that was kind of a coefficient on all those radicals, or something that would reduce with a 22, and nothing does. So we are done. There it is. All right, so give those radicals a try. Good luck.